everyone, and welcome back to another video. Today we'll be reviewing the wave interference and the electromagnetic spectrum practice problems. Let's go and start with number 1. For number 1, you were given multiple statements and you had to determine if each statement was true or false. If the statement was false, you have to correct the statement so it became true. So part A says when two pulses meet up with each other while moving through the same medium, they have a tendency to bounce off each other and return back to their origin. So over here, I just drew an example of two wave pulses moving toward each other, one with an amplitude of 3, as you can see in the blue, and one with an amplitude of 5, as you can see in the red. Before they are moving toward each other, the blue moving to the right and the red moving to the left. During interference, they constructively interfere with each other, as you can see in the purple. And then afterward, they actually do not bounce off each other. They continue to move in their original direction. So for example, the blue was moving to the right before. After interference, it continues to move to the right. And same with the red. The red wave is moving to the left before interference. After interference, it is still moving to the left. So this statement is false. They have a tendency to pass each other after they interfere. Let's move on to part B. Constructive interference occurs when a crest meets up with another crest at a given location along the medium. So we can use the same waves that I drew above. Over here we have two crests. One crest has an amplitude of 3 in the blue, and the other crest has an amplitude of 5 in the red. During interference, they do constructively interfere with each other. They do add up to give you a bigger amplitude. In fact, based on the law of superposition, the amplitude of 3 gets added to the amplitude of 5, giving us a wave sum of positive 8 during interference. And then, as we stated above, after interference, these two waves still move in their same directions as before. And so this statement is true. Constructive interference occurs when a crest meets up with another crest at a given location along the medium. Part C, destructive interference occurs when a pulse with an amplitude of +5 units interferes with a pulse with an amplitude of -5 units. I've drawn this out for you again. So before interference, we have this light blue wave moving to the right with a +5 amplitude and the red wave down below with a -5 amplitude. What happens during interference is these two waves will cancel out. The +5 and the -5 added together gives us 0 due to the law of superposition. And because the resultant amplitude is lower than either of the initial amplitudes, yes, this is an example of destructive interference, and so this statement is true. D, destructive interference occurs when a trough meets up with another trough at a given location along the medium. Let's see if this is true. Again, remember, destructive interference means that there is a decrease in the final amplitude. And so let's see if the magnitude of the amplitude is actually getting smaller as a result of this interference. So I've drawn two waves or wave pulses with amplitudes of -5. So the blue wave is moving to the right and the red wave is moving to the left. And when they move together, we actually add their two amplitudes together. -5 plus -5 gives us amplitude of -10 for the wave sum. And because this is an increase in the wave sum amplitude, this is actually an example of constructive interference. And so this statement is actually false. E, if a pulse with an amplitude of +5 units interferes with a pulse with an amplitude of +3 units, the resulting amplitude of the medium will be +4 units. In other words, it will be average of the two individual amplitudes. So I've drawn this out for you. One has the amplitude of +3, the other wave has an amplitude of +5. Based on the law of superposition, when these two waves constructively interfere, we actually add these two values together. And if we add these two values together, the resulting amplitude of the medium is actually going to be 3 + 5, which would give us +8. And so the resulting amplitude of the medium will be +8. And it should be the sum of the two individual amplitudes. So the original statement was false. F, if a pulse with an amplitude of +5 units interferes with a pulse with an amplitude of -3 units, then neither constructive nor destructive interference occurs. All right, so let's go ahead and apply our law of superposition again. When we have a wave with an amplitude of +5 interfering with a wave with an amplitude of -3, and we add these two values together, the resultant wave should have an amplitude of +2 units. And so because this is a decrease in amplitude in comparison to either initial waves, this is an example of destructive interference. So this statement is false. Then destructive interference occurs, and we can cross out this part. Finally, for letter G, two sound waves could never interfere in such a manner as to cancel each other out and produce silence. If you think about your AirPods, there is something called noise cancellation, and so we know that this is not true. Two sound waves can interfere and cancel each other out and produce silence. Let's move on to number 2. Two waves are traveling along the same medium. The higher frequency wave is moving to the left and the lower frequency wave is moving to the right. I'm going to go ahead and highlight these waves in different colors so that we can refer to them later on in our table. And so I'm going to say the higher frequency wave will be in blue. Remember, higher frequency wave means that this wave will have more crests in a given amount of time, or more wavelengths in a given amount of time. And so that would be the taller wave right here. I'm going to go ahead and trace it. This is our higher frequency wave. And our lower frequency wave, I'm going to go ahead and highlight that one in orange, is moving to the right. So I'm going to go ahead and outline that one as well. Okay, so the orange one is moving to the right, and the blue is moving to the left. So the diagram below shows the waves on the medium at an instant in time. Several of the positions are marked by a letter. Great. So what we need to do here is, in part A, we are asked to find the amplitude of the wave sum. So what we have to do is, for each point, we have to determine what the amplitude of each individual wave is, and then add those points together. Let's go ahead and start with G. So at point G, wave 1 has an amplitude of about 4. Okay, so actually let me go ahead and label this for you. Each unit is 1. And so that's 0, 2, 4, 0, 2, and 4 down below. And these ones are negative. Okay, so I labeled every other line just to keep it neat, not so the numbers aren't too cramped together. Let's start with wave 1. At wave 1 over here, we can see that the amplitude is at a +4. I'm going to go ahead and mark that as green because it is a positive amplitude. And the amplitude for the second wave, wave 2, our orange wave, is about 1.5, which is also above the x-axis. And if we add these two values together, we get a wave sum of about 5.5 units. Let's move on to point H over here. So point H, if we start with our blue wave, wave 1, it looks like it has an amplitude of -4. And label that in red because it is below the x-axis. And wave 2 is still positive, and now it has an amplitude of +1.5. And so if we take the wave sum over here, we can do -4 plus 1.5. That would give us a -2.5. If we move on to point I over here, for I, wave 1, which is the blue wave, has an amplitude of 4 again. And wave 2 has an amplitude of -1.5. Which means if we add these two things together, at point I, the wave sum is 4 plus -1.5, which would give us a +2.5. At J, wave 1 has an amplitude of -4, while wave 2 has an amplitude of negative 1.5. If we add these two values together, we would get a wave sum of negative 5.5 for our resultant wave. All right, I think you get the hang of it. Let's just continue quickly. So K, we see that wave 1 has an amplitude of negative 4. Wave 2 has an amplitude of 1.5. If we add these two values together, it would be negative 2.5. At L, wave 1 has an amplitude of 4. Wave 2 has an amplitude of negative 1.5. And if we add these two values together, we would get 2.5. At M, wave 1 has an amplitude of negative 4. Wave 2 should have had an amplitude of negative 1.5. Adding these two values together would give us a negative 5.5. At N, wave 1 would have an amplitude of 4, while wave 2 had an amplitude of 1.5. Adding those together would give us 5.5. And then finally at O, wave 1 has an amplitude of negative 4, and wave 2 has an amplitude of 1.5. Adding these two things together would give us a negative 2.5. Now, part B wants us to identify which letters show examples of constructive interference and which ones show examples of destructive interference. And so the reason I color-coded above the x-axis as green and below the x-axis as red is so that we could tell if these two waves agreed in the direction that they were pointing in, or if they were in opposite directions. If they're in the same direction, meaning they're green and green or red and red, that is constructive interference because they're going to be added together and give us a greater amplitude. If they're in opposite directions, as in red and green or green and red, then they would destructively interfere, giving us a smaller amplitude than either individual wave. All right, so let's go ahead and start with G. At G, they are in agreement, so this is an example of constructive interference because they are both in the green. For H, because one is negative and one is positive, this is an example of destructive interference. For I, because one is green and one is red, this is also destructive interference. For J, because they're both red, this is an example of constructive interference. For K, because one is red and one is green, this is an example of destructive interference. For L, same thing, one is green and one is red, and so that's destructive. For M, they are both red, they're both in the same direction, that is constructive interference. For N, they are both green, they're both in the positive, that is constructive interference. And for O, because they're in opposite directions, one is red and one is green, that is destructive interference. So as you can see, the examples of constructive interference would be letters G, J, M, and N, and the examples of destructive interference would be letters H, I, K, L, and O. I just wanted to clarify that destructive interference means that there is a decrease in the amplitude as compared to the wave with the highest amplitude, and so let's go take a look at that. For example, for point H, the highest amplitude would be a negative 4, and the wave sum is lower than that, which is a negative 2.5. For I, the wave with the highest amplitude would be wave 1, an amplitude of 4, and the wave sum is 2.5, which is lower than that. And so it does not mean that the wave sum is lower than the amplitude of both of the waves, but rather it is lower than the amplitude of the wave with the highest amplitude. In other words, the wave sum has an amplitude that is lower than the wave with the highest amplitude. Let's go ahead and move to number 3 over here. The diagram below represents two identical pulses approaching each other in a uniform medium. What is the maximum amplitude of the medium when they meet? Well, we can see over here that pulse A has an amplitude of 3 and pulse B has an amplitude of 3, and so when they meet in the middle, you would add these two displacements together for an amplitude of 6 centimeters. This is due to the law of superposition. For number 4, two speakers S1 and S2 produce circular wave patterns as shown in the diagram below. Let's start with A. So actually before we get to that, remember that with sound waves, they're actually longitudinal waves. And longitudinal waves have rarefactions and compressions. Compressions are kind of like crests. They're like high points. And rarefactions are kind of like troughs, the low points. Okay, so when we're talking about constructive interference, that means that we either have two troughs or two rarefactions that are passing through each other, or we have two compressions that are passing through each other. For destructive interference, that means that we have a rarefaction that is bumping into a compression, opposite things. So let's keep those terms in mind as we're talking about this problem. So at which 2 points is constructive interference occurring? Let's just go through letter by letter. We'll just say that constructive interference, I'm going to underline in a green, and destructive will be red. So starting with A, over here we have dashed lines passing through point A. Okay, so here's point A. We have two dashed lines passing through. That means we have two rarefactions that are passing through each other. Therefore, since they're both in the same direction, they're both rarefactions. That means we have an example of constructive interference. So A would be an example of constructive interference. How about B and C? Well, B and C are right here. And if you can see, for both B and C, we have one dashed line passing through. Okay, and we also have solid lines passing through. In other words, we have a compression and a rarefaction affecting points B and C. And so since those are opposites, these are examples of destructive interference. So B and C are destructively interfering. Finally, we have point D. Point D, we have two solid lines that are passing through point D, and these represent compression. Since we have two compressions passing through each other, that is going to be an example of constructive interference. So let's move on to B. At which 2 points would the listener hear the loudest noise? And how about the softest noise? So with constructive interference, you know the amplitude's getting bigger. Okay, so an increase in amplitude compared to the highest amplitude. And with destructive interference, we have a decrease in the amplitude from the highest amplitude. So that means something would be getting quieter, because amplitude relates to sound intensity and therefore how loud we perceive the sound to be. And so the 2 points where the listener would hear the loudest noise would be at A and D, and the softest noise would be at B and C. Now, how about the loudest noise between A and D? Well, remember that sound dissipates as you get farther and farther from it. So between A and D, forgot to circle D with the green before, but between A and D, which of the two is closer to the speakers? Well, D is closer to the speakers, and so D would be the loudest between those two loud points. So let's go ahead and move on to number 5 over here. Which wave characteristic is the same for all types of light traveling in a vacuum? So remember that light is on an electromagnetic spectrum, which means that different light forms are characterized by their different wavelengths. And so therefore, all types of light do not have the same wavelength. Well, wavelength actually affects frequency, because the shorter the wavelength, the higher the frequency, and frequency is related to time, which is also related to the period. So all three of those things are not the same. If you remember from our electromagnetic radiation lecture, we also know that wavelength is related to energy. And so as your wavelength changes, your energy also changes. The only thing that's staying the same would be the speed. And remember, the speed of light, the speed for all types of light is the speed of light. Which is 3 times 10 to the 8 meters per second. So how about number 6? Which wave characteristic is the same for all colors of light traveling in a vacuum? So this one's a little different from 5 because we're talking about colors of light, so we're talking about visible light. Let's see if our answer is the same or not as compared to number 5. So colors of light are different because they all have different wavelengths, which means, again, it affects the frequency and the period and also the energy that each wave carries. And so the only thing staying the same between all colors of light is, again, the speed, which is the speed of light. Let's go ahead and move to number 7 over here. So orange light has a wavelength of 600 nanometers, which is also 600 times 10 to the negative 9 meters. What is its frequency in hertz? And hint is to remember the speed of light. So let's go ahead and write out our givens. We are given that the wavelength is, I'm just going to go ahead and use the meters because that's standard notation, 600 times 10 to the negative 9 meters. We also know that the speed of light is 3 times 10 to the 8 meters per second. What we're trying to find here is the frequency. The equation we can use is that V is equal to frequency times wavelength. And we're trying to solve for frequency. I'm going to change this equation around so it's frequency equals V over wavelength. If I substitute, that would give me 3 times 10 to the 8 meters per second divided by the wavelength, which is 600 times 10 to the negative 9 meters. And if I solve for that, I would get the answer of 5 times 10 to the 14 meters. And finally, we have number 8. Calculate the wavelength in a vacuum of a radio wave having a frequency of 2.2 times 10 to the 6 hertz. Remember the speed of light. So let's again start with our givens. We are given the frequency, which is 2.2 times 10 to the 6 hertz. We also know that the speed of light, which is the speed that all light is traveling at, as reviewed in numbers 5 and 6, is 3 times 10 to the 8 meters per second. Our unknown here would be the wavelength. We're going to use the same equation, V equals frequency times wavelength. In this case, we're trying to solve for the wavelength, so I'm going to change the equation around. Divide both sides by the frequency to isolate wavelength. And so wavelength equals velocity over frequency. If I substitute, wavelength is going to be equal to 3 times 10 to the 8 divided by the frequency, which is 2.2 times 10 to the 6. And if I plug that into my calculator, I would get the answer of 136.36 meters. All right, I hope this video was helpful in reviewing the practice problems. Feel free to let me know if you have any more questions, and I will see you in the next video. Thanks for watching. Bye!